All right, this is 24.2, forces caused by magnetic fields. We'll learn how to calculate the force, the magnetic force on a current-carrying wire and for a charged particle. Also talk about galvanometers and electric motors. No, that could be galvanometers or galvanometers. All right, so magnetic force. Magnetic force only affects moving charges. So it affects a wire when it has current because the electrons in it are zipping through the wire. Magnetic fields will interact with other magnetic fields or magnetic objects. So right here I have some magnets which I'll pass back, right? They're going to repel. So they interact with each other with magnetic fields. They will interact with magnetic objects, such as paper clips. And they will interact with moving electric charges. And you can pass those straight back. Yeah. There is a way of finding this magnetic force by using the right-hand rule. There's like, in your book, 4 right-hand rules, but they're all kind of the same. Your thumb will always be that moving charge, so whether it's current or whether it's just a particle that's moving, that will be your thumb. As long as it's moving. If it's not moving, then it's not going to be interacting with it. Your index finger is the magnetic field, B. And now, the one that we didn't go over yesterday was the force. We're adding that. Force is your middle finger. Middle is force. So let's do a little practice here. We have current this way and magnetic field this way. So put your thumb in the direction of current. Put your middle finger in the direction of the magnetic field. And then you'll see that force, your middle finger, and I just keep all 3 together so it doesn't look like I'm doing anything bad. 3 straight up. It's perpendicular. It's 3 dimensions. One point's one way, this one's 90 degrees, and this one's 90 degrees to both of them. So if this is I and this is B, your force is going to be upwards. So this is force. Out of the force. Now, a lot of times when we're talking about wire, it'll just ask you which way the magnetic field's going. Is it going clockwise? Is it going counterclockwise? And you don't need to worry about the force. But if it does ask you about force, you need to add that 3rd dimension in there with the middle finger. The rest of your finger. Fold your hand. Okay, are we ready? Let's see any cups today. So here is how to calculate the magnetic force on a wire. The force is going to be equal to the current times the length of the wire times the magnetic field. So current is in amps, length, that's the L here, is going to be in meters. Make sure it's in meters and not centimeters. And then B, which is our new variable, that's the magnetic field, and it's measured in Teslas. Yes?
For that, is it supposed to be B and B, and it's supposed to be B? For middle is force, still B.
That's supposed to be F. For force. Thank you. I'll fix that. Force. There you go. like the field feeling. Oh, you already have one? Okay, we're going to look at some pictures. So this is kind of what we went over yesterday, is that you reach out and grab the wire in the direction of the current. So if the current's going up, we would reach out and grab this wire and see that the magnetic field, if you're looking down at it, is going to go counterclockwise. And then if it's going down, put your thumb down and you see that it's going clockwise. So that's what we learned yesterday. Now we need to apply the force to that. So here is an example. We have current down here at the bottom. We have current going this direction, so put your thumb in the direction of I. Now your magnetic field always from north to south, so your magnetic field points this way. And then curl your fingers upwards. That is the force. So the force on this wire, as long as you have a current going through it, if we're going through this magnetic field, the wire itself is going to be pushed upwards. If we turned the current down to the other direction, we flipped it around, and we had our magnetic field in the same direction, then our force would be down. Now, sometimes when you have two wires next to each other, they'll either be repelled or attracted, depending on their current. Now, you would think that if the current was in the same direction, because opposites attract and like repel, they would actually be pushed apart. But they're not. They're actually attracted to each other. So in this one, we have I going up. So over here we have the magnetic field going counterclockwise. And here we also have it going counterclockwise. So why do they attract? Same magnetic field, same current. Why are they attracted? Look at the picture here. Look at the magnetic fields. On this side, it's the right side. So, and the magnetic field goes around and goes into the board. And on this side, it's the left side of the wire. So when the magnetic field comes around, it's out of the board. So we have into the board and out of the board. Those are opposites. So that's why they attract. Magnetic fields, even though they're in the same direction, because they're different sides of the wire, they're opposites and they will together. So look at the other side. We have current going this way, so it's counterclockwise, and then we have current in the opposite direction, so it's clockwise. And they are going to repel each other. Even though they're opposite directions, here we have into the board, and here we have into the board, so they repel each other. So these two wires are going to push apart. Questions about that? Oh, hey, let's go on to galvanometers. Galvanometers? I think it's galvanometers. All right, it is used to measure very small currents. So when you have a magnetic field and you move it past the wire, it pushes those electrons. It's not going to push them very much. It's going to be very, very weak current. So any current caused by a magnetic field, unless it's like a huge magnetic field, is not going to be very much. So we need a very sensitive device to do this. Instead of using an ammeter, they use a galvanometer. It is very precise. It measures very small things. And this is how it works. We have a nice loop here in a magnetic field. And when we hook this loop up to the rest of our circuit, right, this is in the meter. We hook it up to our circuit, it takes that current and pushes it through the loop. And as soon as it goes through that loop, it's in a magnetic field. So if this is the current on the left is going this way, and our magnetic field is this way, we've got our thumb here, our magnetic field this way, the force is down. So on this side, it's going to be down. When it comes around this way, our force is still this way. Force north to south. got our I going this way, so our force is up. So up on this side, force down on this side, it causes it to turn. And we can measure how much it turns. This is connected to a spring and a coil, right? And that will tell us, that'll move the needle and tell us how much current is running through it. So depending on how much it tilts in that magnetic field, will tell us how much current. Okay, you guys ready for the next slide? Okay, electric motors. So this same idea is used in an electric motor. You can see that we have a current. It's hooked to our little metal loop, which we call a split ring communicator. The current goes through. Here's our magnetic field. So if our current's this way, and our magnetic field is north to south like this, the force will be down. So on this side it's down, and then we turn it around. This is the current this way. Our magnetic field is this way, and our force is up. So we have force down here, force up there. It's going to cause it to spin. So I have a very simple motor right here. We have a battery with 2 safety pins. To the other side of I have a rubber band holding that on there. This is a big coil of wire, not a big one, a little coil of wire. And it has this bright orange shiny stuff we see is actually insulation. So it's got like a little coating of insulation on it. On one side, I have completely stripped the insulation off, so you can just see the exposed copper wire. On the other side, I only have half of it stripped off. So this bottom part here has got insulation and the top doesn't. So when I flip this over like that, it completes the circuit. But when it comes over here, it has insulation blocking it, so it doesn't complete the circuit. Now watch what happens when I put it in a magnetic field. Oops. 1 second. I gotta separate these magnets. Otherwise it's too strong. Maybe I can't. Alright, so I have my little magnet right here. And you can see it's spinning. Isn't that exciting? So how come I need one side of those to only be half of it attached to it? What would happen if I had it all stripped on one side? If it just made the circuit the whole time? Probably wouldn't spin. Okay, so it would just sit there, and it would be attracted to the magnet or repelled to the magnet, and it would hold. It wouldn't do anything. So the reason that it's only halfway, why only one side has insulation and the other does not, is because this magnetic force pushes it, and it holds it there. So as soon as the current stops going through it, it lets it fall again. So on one side, the magnetic field pushes it up, it breaks the circuit, and gravity pulls it back down. And then the magnetic field pushes it back up because it makes this current again, and then it stops the current and it falls back down. So without that breaking the current, then it wouldn't work. Now this could be why alternating current is so important, because it causes the current to go from one direction to the other. So as it's going one direction, it pushes it up, and then it turns direction and it's going to push it back down. So you could have a motor like this without using gravity if you had alternating current coming from this battery. So like if I plugged it into the wall, because current goes one way and then it goes the other. So see why current is really important for motors, the alternating current one? Because when it goes this way, magnetic force pushes it this way, and when it goes this way, magnetic force pushes it this way. So that allows it to go up and then come back down. and over and over and over again. All right, charged particles. Enough about current. Let's talk about charged particles. Magnetic fields can apply a force to moving charged particles, not standstill particles. If the particle isn't moving, it won't be affected by the magnetic field. Charged particles are used in those old school CRT monitors and the big fat TVs with the big back on them. It receives a color map from your cable box or from your satellite or from your video, and that tells it how to create the magnetic field. And as these particles get projected into, as they fly into the magnetic field bends them into the correct place so that you see a nice, pretty screen. Now, static makes more sense because if your cable box isn't giving a full picture, or the signal is messed up, that's going to mess up the magnetic field, which when the particles go and hit it, they're not going to be the right spot. They're all garbly good. Your noise. Now you can still use your right-hand rule on this. Your moving charged particle is still going to be your thumb, so I and Q are going to be the same thing. Your magnetic field is still your index finger, your hand. And then when you bend your fingers, that's going to be the force. All right, here's a picture of one of those screens. You've got your red, green, blue electrons there. So if the particles are moving this direction, your magnetic field, depending on which orientation, is going to send your particles in the correct direction. So here's how to calculate it. F equals QVV, where Q is charge, usually the charge of an electron. V is the velocity of that electron, that'll tell you how fast it's going. And B is your magnetic field measured in teslas. Last little slide of information here. I'm sure that you've heard of a hard drive, that magical little thing in your computer that makes it work. A hard drive stores information using magnets. So it takes the electron and orients it this way, and that's a 1, and then orients it this way, and that's a 0. And that's what your computer reads, and that's how it stores its data. So you never want to put a magnet near the hard drive unless you're trying to get away from the government. You want to destroy your computer. Erasing it on your computer doesn't really completely and utterly erase it. Blowing it up, I mean, still, if they find a piece of it, they can still get information off of it. Lighting it on fire, unless it's hot enough to melt the hard drive, probably not going to protect you. So, you're trying to hide something. Take your hard drive out, take it out of its little metal case, find the little discs on it, and take a really nice strong magnet and just wipe it right across there. It takes all those 1s and 0s and makes them all 1s, makes them all 0s. If you're ever trying to hide, how to do it. If you don't trust the government, don't trust your computer. All right, I want to get to the practice before people have to leave. So I have 2 little practice questions for you today. Oh, it's Friday. All right. Whatever. It's okay. That stuff wasn't important anyway. Just interesting to, like, conspiracy theory stuff. Okay, our first one says a current of 2 amps is traveling on a 20-meter long straight wire to the north. Write this down as we talk about it. 2 amps, 20 meters north. What is the magnitude and direction of the force produced by the wire if the magnetic field is 2 Teslas and directed east? So what's the 2 amps? Current. 20 meters. Right? So that's L. And what's the 2 Teslas? B. And that is the magnetic field. What are we looking for? Force. And our equation? I-L-B. Good. Now we have everything. We know what we're looking for, so let's plug that in. F is going to be 2 times 20 times 2. So force is 80. Now it's magnitude and direction. So we found magnitude. We got to use our right-hand rule to find direction. If the length of the wire is north, that means our current is north. And then a magnetic field is directed east. So put your thumb in the direction of the current, your magnetic field that way, and then curl your fingers, and your fingers go up. So out of the board is force. So if this is north and this is east, this would be up. Thank you. Nope, that doesn't look good either. F is upward. Right. I, B, F. What? Yes. East. Thank you. They didn't catch that in the other class. That they just trust everything I say, which that should never happen. All right. East. I. This is B. So that means that it's the other way. I, B, F. So this is into the board. Usually like an X or something. In. So F is into the board. I cannot believe I didn't catch that earlier today. All right, so this would be down. I don't know why I put east west earlier. That's exciting. All right, an electron traveling at 1.7 times 10 to the 8 meters per second north. Let me write that down. 1.7 times 10 to the 8 meters per second north, south, north. Through a magnetic field of 4 Teslas directed west, what's the magnitude and direction of the force? Okay, so what's this 1.7 times 10 to the 8 meters per second? Velocity. And 4 Teslas. The magnetic field. What are we looking for? What's the question? Force. Magnitude is the number, direction is the north, south, east, west. Okay, so what equation do we want to use? F equals QVB. We're missing something. Q, what's Q? Charge of the electron, which, does anyone remember it? It's okay, I do. 1.6 times 10 to the negative 19 coulombs. So let's plug this in. We have F equals 1.6 times 10 to the negative 19, 1.7 times 10 to the 8, and 4. And I get 1.09 times 10 to the negative 10 newtons. Now let's look at direction. We have an electron traveling north. So this is our electron charge is north. Our magnetic field is west, which is to the left. Thank you, west. That's supposed to be B. There we go. So if the electron is traveling north, that's your thumb. Magnetic field this way, and your force is out of the board. In other words, upward. How do you feel about this stuff? It's not that tough. Could be. All right, I have 5 clicker questions for you today. Here's the first one. If the direction of the conventional current flowing through a wire is from bottom to top, what will be the direction of the magnetic field relative to the wire?